We learned about the concept of dispersion in the last lesson and also one measure of dispersion, namely range. Range was easy to compute but suffered from lack of robustness. It used the data points too superficially. It was completely determined by the two extreme values and did not care about the rest of the data in between. In this lesson, we shall learn about two related measures of dispersion that are free of this problem. The measures are called variance and its square root, the standard deviation. These are by far the most popular measures of dispersion. Let's learn about them step by step. Let's take a moment to remember why we are caring about dispersion. We have a bunch of numbers with central tendency, and we want to represent the bunch with a single typical value. We are wondering how well this single number can represent all the data values. The higher the dispersion, the less reliable is the representation. This was our motivation for considering dispersion. Let's turn this motivation into a measure of dispersion. Let the numbers be called x1, x2, etc. So the ith number is xi. Let's use mean as our central tendency measure. So this is x bar. Now we are trying to check how well this x bar is going to represent all the different xi's. If xi is close to x bar, then the representation is quite acceptable. But if xi is further away from x bar, then the acceptability is dubious. So the difference between the point and the center plays a crucial role in determining how well the mean can represent the point. Let's focus on the ith point. Its difference from the mean is xi minus x bar. In this case it is negative because the point is on that side. Had this point been on this side, then of course it would have been positive, but we here do not care about sides. So we want to get rid of the sign, and one way to get rid of the sign is to square the difference to get xi minus x bar whole square. For each point we get one such number. Now we want to get a single number, a typical number to represent all this. That again sounds like a central tendency problem. So we can again take the mean of all these numbers to get this quantity. This might look complicated. Had we not followed its genesis, it would have left us wondering, how does this formula qualify as a measure of dispersion? But now of course we know this is called the variance, and its square root, as we already know, is called the standard deviation. Let's quickly digest the definition with a small numerical example. In this broadcast, we are going to see hand computation of variance using the definition. So I have my numbers here, 3, 5, 4, 5, 1, 7. So quickly counting, I see that there are 6 numbers. So sample size here is 6. Okay, the first step will be to compute the average, for which I will first need to add them up. 8 plus 4, 12, 17, 18 plus 7, that gives me the total 25. So I get the average, which is x bar, that will be 25 divided by 6, whatever that is. The next step is to subtract this x bar from each of these values, and I want to create a new column with those numbers. Here my x bar is roughly 4.17, so when I subtract, this is my x1 minus x bar, 3 minus this 4.17, that is minus 1.17. Similarly, 5 minus 4.17, 0.83, and we can fill up the rest of the numbers in the same way. So I have minus 0.17, 0.83, minus 3.17 and 2.83. Okay, so the next step will be to square all these things and then add them up. Because the formula is xi minus x bar whole square, you sum them and finally we are going to divide it by n. So I shall create another column here that will contain squares of these numbers. So here I shall write the square of this number, which is approximately 1.37. Let's similarly fill up these places by squares of these numbers. So we have got all these numbers xi minus x bar whole squares. Our next job is to add them up. That is, I want to find the sum of this entire column. This total turns out to be 20.84. Now here is a little word of warning. When I am writing things like this, I am rounding them off to 2 decimal places. I have just chosen this level of precision arbitrarily. Now, when I am rounding this off to 2 decimal places, I get this. Now, when I square it, I again have to round it off. So, I am actually rounding it off at every step. Since I am using rather crude level of precision, say just only 2 decimal places, the result might deviate somewhat from the actual value. Now, when we use a calculator, in fact, I am using a calculator behind the scene. In that case, you will get more precise results and there is no need to round off the intermediate steps. So, if the calculator gives you 10 decimal places, you should actually continue your computation with 10 decimal places and round it off only at the very end. But here, in order to show the things, I am rounding things off at every single step. So if you do the entire computation using a computer or a calculator, your answer may be slightly different from what I am getting. Okay, so the final thing is this quantity divided by n, that is this divided by 6, which turns out to be 3.47. So that is the variance of these numbers computed directly using this definition. Okay, so let's now compute standard deviation, which is simply its square root. Square root of this variance turns out to be roughly, again rounded off to 2 decimal places, 1.86. So you see, this computation is not very complicated, but at the same time, it's not very interesting either. It is a bit tedious.